Today, class, we're going to be talking about free fall and what that really means in terms of our physics understanding of it. Let's take a look. So if you're like me, you think about free fall and you look at this skydiver here and think, well, anything that's going to be freely falling out of the sky is going to be something that's in free fall. And that is true under certain circumstances. It's often used in that skydiving, but in terms of physics, it actually has some specific meanings that we need to go over. So when we talk about it for physics, though, it actually has a specific definition of some conditions that we need to define. For example, when I launch this soccer ball straight up into the air, the whole time that it's in the air and when it comes back to my hand is in free fall conditions. And so is this basketball that's being shot. Once it's released, we will consider that to be in free fall condition. So what does it really mean then to be in free fall condition for us in terms of physics? If you were to look up in your books and find a definition for free fall, most likely you would find that it would say that there's only one force acting on the object, and that is the force due to gravity. And that's a fine definition and explanation. However, at this point, we haven't really defined what a force is. So it is gravity that is pulling us to the earth when we talk about objects falling from the sky. But another way for us to define it at this point with our understanding is to say that when the object is in the air and it is not touching another object, we could say that it's in free fall conditions. So it doesn't really matter whether it's going up or going down. If you look at this soccer ball, right, as soon as I throw it up and it releases from my hand, it's actually in free fall conditions. The whole time that it's on its way up, even the momentary split second that it stops at the top, and right until it actually hits my hand, the moment right before it hits my hand, we would say that it's in free fall condition. There is another aspect that we have to define that works here as well, and that is that we have to ignore air resistance. So we're ignoring all air resistance, and this is how we're able to say that the force associated with the wind resistance or the drag, this is referred to in aeronautical terms, is not actually acting on the object because we're in a vacuum. In fact, you'll often hear me refer to it as like a breathable vacuum. So from this point forward in the course, with our understanding for physics, we're going to assume that we're always operating in a vacuum, in this breathable vacuum. And really what we're doing is we're ignoring the resistance due to air. When you go back and think about those skydivers in the real world, as they jump out of the plane, they are continuing to accelerate down, speeding up as they're falling to the earth due to the force to gravity. But there's another force that's actually acting back on them in the opposite direction, and that's this resistance due to the air molecules, or what's referred to, again, as I said, as drag. Eventually, they reach a point where the resistance due to the wind in the air is so great that it actually equals the force of gravity that's pulling down, and they actually balance themselves out. And at that point, they're no longer gaining speed. They reach what's called terminal velocity. And at that point, the skydiver will maintain the same velocity, a constant velocity, as he continues to fall to the earth until he pulls his parachute, in which case, obviously, he would start to slow down. But for our purposes, again, remember, we're going to be ignoring all air resistance. And by doing so, that enables us to understand that all objects, independent of their mass, will accelerate at a constant rate down when they're in the air due to the force of gravity. And that acceleration is going to be what we refer to as little g. And the magnitude of little g is 9.8 meters per second squared. And the direction of that is going to be right down towards the center of the earth. So no matter where you are on earth, now the acceleration due to gravity may vary at different points throughout the earth, but it's accepted to be at 9.8, and it's going to be constant in a localized area here on the earth. So within that region, what we're going to assume is that when you're in free fall conditions, you're going to have every object that's not touching anything else, that's in the air, is going to be accelerating down towards the center of the earth at the magnitude of little g. Since we have a constant acceleration, all of the uniformly accelerated motion equations will apply for free fall conditions. Now, if we're looking at the acceleration in the y direction, again, this is our frame of reference that we're saying the up is positive and that down towards the center of the earth is the negative direction, and that's the way we want to define our frame of reference, then we would say that the acceleration in the y direction is actually negative g, making it negative 9.8. But please understand that g, the acceleration due to gravity, is not negative 9.8. Little g is 9.8 meters per second squared, and then when we apply a negative y direction, we find that the acceleration in the y direction down towards the earth will give us negative g, or negative 9.8 meters per second squared. One other thing that I want to point out is that you do not have to be falling. Okay? Free fall conditions do not mean that you have to be falling. So if an object is traveling up and horizontally, as we will get into projectile motion, it doesn't really matter if you're going up or you're going down. If you are in the air and you're not touching another object, and the only force acting on you is gravity, because we're in this breathable vacuum, then you're in free fall conditions, and your acceleration will always, throughout the entire time you are in the air, will be 9.8 meters per second squared straight down. So again, just to recap here, the only force acting on an object that is considered to be in free fall conditions will be the force due to gravity. You will be in the air, the object will be in the air and not touching another object. That entire time period will be considered free fall conditions. We are ignoring air resistance from here on out unless otherwise stated in the problem. Everything will be then in free fall conditions, accelerating at 9.8 meters per second squared down towards the center of the earth. And if we put our negative and positive frame of reference for the vertical orientation, the acceleration in the y direction would then be negative g, and making it negative 9.8 meters per second squared when you're trying to solve these free fall problems. And you do not have to be falling. Okay? Thank you, and I'll talk to you soon.